In this example, we will explore the feasibility of pursuing a fast follower for buspirone, a 5-HT1A ligand used as an anti-anxiolytic therapeutic. Buspirone has a known liability due to rapid metabolism by CYP3A4, leading to low oral bioavailability and a short half-life in man. The project wished to efficiently identify analogues of buspirone with an in vitro CYP3A4 half-life 3 times longer and a minimum loss of receptor affinity. The structure of buspirone can be broken down into 3 regions: an aryl piperazine, a tetramethylene linker, and a piperidine-dione moiety. The objective is to identify structural modifications that reduce the vulnerability of key sites of metabolism, as indicated by decreasing the site lability, and ultimately identify molecules that are likely to meet the project goal of increased half-life with respect to metabolism by CYP3A4 by reducing the composite site lability, or CSL. We will explore modifications to the different regions of buspirone identified previously, using 2 different series. S1 will explore alternative aryl substitutions on the piperazine, and S2 will explore modifications to the tetramethylene linker and piperidine-dione moiety. These series were designed to maintain potency against 5-HT1A as well as improve metabolic stability. First, we open the file buspirone S1 using the File Open menu. This contains the compounds in Series 1. In the table, you can see the compound structures, identifiers, and their measured half-life with respect to metabolism by CYP3A4. The table contains 9 compounds, the first of which is buspirone. We change to the P450 tab and then select all of the compounds in the dataset by clicking in the top left corner of the spreadsheet, and we submit these to the P450 models by clicking on the arrow button. When the calculations are complete, the results will be returned from the server and a summary will be displayed in the spreadsheet. Each molecule takes roughly 1 to 2 minutes to calculate. However, if the results for a molecule have previously been calculated on the server, as is the case here, the results will be returned instantly. Selecting a row in the spreadsheet will display the detailed results for a single molecule in the P450 tab. We can look at the different results in turn to identify modifications to the aryl group that improve the vulnerability of this region of the molecule to metabolism by CYP3A4. This will be indicated by lower site lability bars shown for the corresponding sites in the metabolic landscape view, example of which is shown here. The composite site lability, or CSL, for a molecule is a measure of the efficiency of the product formation step in the catalytic cycle of CYP3A4. Thus, a lower CSL value indicates greater stability. In this case, as we are modifying only one region of the molecule, other moderately labile sites remain, so there may only be a small change in the overall CSL, even for a beneficial modification. Also, other factors influence the overall rate of metabolism, in particular log P and pKa. Therefore, we do not necessarily expect a direct correlation between the small changes to CSL and the CYP3A4 half-life at this stage. Open the file buspirone S2, again using the File Open menu. This contains the compounds in Series 2. We run the P450 calculations as before, so that we can explore the resulting metabolic landscapes and look for examples where we have managed to reduce the site labilities on the tetramethylene linker and the piperidine-dione moiety. An example of this is shown here. Finally, we would like to explore combinations of the modifications we have identified to find compounds with improved overall stability, while avoiding those changes that caused a large decrease in potency. We open the file Combined to load 3 such examples so that we can run the P450 models on these, as before. Note that all of these compounds have significantly lower, or better, CSL values than buspirone and meet the objective of greater than 3 times the half-life. Furthermore, in 2 cases, IC50 values against 5-HT1A of less than 0.1 micromolar have been retained. If we want to try out further ideas, we can very quickly create new molecules in the Design tab. Having designed a molecule we'd like to explore further, we can easily add this to our dataset by clicking the arrow button. To try this for yourself or to see more worked examples of some of StarDrop's other features, take a look in the tutorial section of the Optimising community.